All right, so we start out with this ping pong ball. It's going back and forth, okay? We're not looking at whether it's moving up and down or whether it's moving side to side across the table. We're only looking at forward, backward between the two people, okay? So we're not bringing any other movement, just left and right into this. So we're simplifying it quite a bit. All right, so it's hit back and forth across the table, okay? And it first travels 3.2 meters to the right at 4.1 meters per second to the right. Okay, so the first thing we got to do is write down all of our givens, and anytime you've got a question that's got more than one part, you split it up into the parts. Okay, so we know the velocity was 4.1 meters per second, and that the displacement, it was 3.2 meters right. These are both to the right. Okay, and that's how, of course, I know that they're velocity and displacement, because they have direction on them. I'm not going to mistake them for distance and speed, which are scalar quantities. All right, it's then returned at a velocity of 5.3 meters per second to the left. So that's going to be part 2. Oops, sorry, that's a velocity, not a displacement. All right, and we don't know d, but we're told that it travels for 0.8 seconds. Okay, and then for part 3, okay, we're told that it's hit back to the right at 6.4 meters per second. So probably smashed, okay, so it's moving really fast, and traveling 4.1 meters to the right. Because if you ever watched, like, people who really know how to play ping pong, they stand like 2.5 meters back from the table when they play. Like, you or I would be right here, serving and playing, but really good ping pong players are like this far back from the table. Okay, it's crazy to watch people who are really good at ping pong. I once played it in intramurals at university, because the dorm I was at, we did every intramural activity, the swim meet, the ping pong thing, all of it. And I came up against this guy who looked like he really knew. He had his own paddle. That was the first sign that he was probably pretty good. And then he started stretching. And I'm like, I was a pretty good athlete, but I wasn't going to warm up and stretch for ping pong. I didn't think it was necessary. After that game, I realized it was important to warm up and stretch to play ping pong. He beat me 21-2. And my 2 points weren't because I did anything right. He just tried crazy serves that happened to not get over the net, and I got points for them. Okay, this guy was really good. All right, so and that's what we're looking at here. We got, really fast action in ping pong here. All right, I want to find the total distance traveled. Can I do that right now with the information that I have? No, I need to calculate what? Right. I need to calculate the distance / displacement in part 2 here. All right, so I'm going to calculate the vector quantity, and then I'm not going to worry about the vectors after that, because distance is obviously scalar. All right, so I know that the time is 0.8 seconds, and I know that the speed is 5.3 meters per second, so I'm going to manipulate v equals d over t to solve for d. All right, how do I do that? Right, so I multiply both sides by t. T comes over here, and now I'm solving for d. All right, so we're going to have 5.3 times 0.8 seconds, right, and that'll give us our displacement for that part of the question. Okay, 4.24 meters is how far he travels to the left in part 2. All right, so now can I calculate the total distance traveled? All right, what do I do? Okay. Right, I add up all the d's, not caring whether they are left or right, okay, because distance is scalar. All right, so the total distance traveled, okay, is going to be 3.2 plus 4.24 plus 4.1. So plus, what is it, 3.2 and 4.1, right? All right, so the total distance traveled by the ping pong ball is 11.54 meters, okay, during this particular rally. Okay, that part ringing a bell for everybody? All right. I want to calculate average velocity. What two things do I need? I need the total displacement and the total time. Okay, because remember, average velocity, we talked about this last week, whenever you have a multi-part question, okay, we're talking about total over total. All right. I don't have times for part 1 or 3. Can I get them? Yes, I just have to do a little v equals d over t manipulation, right? Okay, so v equals d over t, and I want to solve for t. This is the tricky manipulation of that formula. What do I have to do with t? Right? Just like I did before. Right, and then I divide by v to get it over here. Okay, I can't just move d over because that won't solve for t. It'll solve for 1 over t, which is not the same thing. All right, t has to be, on, or anything for that matter, has to be on the top of an equation if you want to solve for it. All right. Okay. So t for this part of the question will be 3.2 divided by 4.1, because this is our meters and this is our meters per second. And when we divide those, the meters cancel and leave us with seconds. Okay, so we'll have 3.2 divided by 4.1. So 0.78 seconds. All right, so the time here is 0.78 seconds. All right, got to do the same thing over here in part 3. T equals d over v. 4.1 divided by 6.4. Okay, which is probably why this rally ended. It'd be pretty hard to have a reaction time and affect the movement required to hit the ball in 0.64 seconds. Okay, I've got d and t now for all 3 parts. Can I do the average velocity now? Okay, what do I have to be mindful of with the d's? Right and left. Okay, average velocity is a vector quantity, so I'm going to make right positive and I'm going to make left negative. Okay, in other words, I'm going to subtract the numbers that are left. Okay, everyone follow me on that? All right, so when we go back down to here, okay, we're going to have average velocity is going to be 3.2 minus 4.24 plus 4.1, okay, and that is going to be divided by 0.78 plus 0.8 plus 0.64. Okay, everyone with me there? Okay, remember that the times all get added together no matter what, right? Because time is not vector, time is scalar, okay? Just because I went backwards distance-wise doesn't mean I went backwards in time, okay? If you ever subtract time, that's what you're saying you did, okay? Just went backwards in time. All right, so we'll have our 3.2 minus 4.24 plus 4.1, okay, divided by 0.78 plus 0.8. Whoop, I better put that in brackets or I won't know what to do. Okay, plus 0.64. All right, so we're getting an average velocity here of, let's say, 1.38. What are my units? Meters per second. What's my direction? Right. Okay, is that ringing a bell? Okay. What would this look like if I graphed it? Since that's what we're moving on to this week. If I was going to make a graph of what happened in here, okay, remember that a graph has two axes. What are the axes? X and Y. Okay, so which one's X and which one's Y? Please? Right. The horizontal one is X, okay, and in fact this is positive X, okay, and the vertical one is Y. This is positive Y, and down here would be negative Y. Okay? It is okay for a graph to go into the negatives. You might not have dealt with that yet, but you will here in Science 10. All right, which thing, displacement or time, should go on the x-axis? Holly? Time. Okay. Basically, guys, I have never seen a graph where time went on the y-axis. Okay, because that would mean that something I was doing was changing the flow of time. Okay, because when we have an experiment, the manipulated variable always goes on the x-axis, and the responding variable, the one we're trying to change by doing something, okay, goes on the y-axis. Now, you might also think, Coder, you're not manipulating time. Well, actually, I am. Not in a way of making it run faster, slower, forwards, or backwards, but in I'm choosing how long my experiment runs for. In that way, I've manipulated how much time the experiment has to run. Okay, I could make it 5 seconds, I could make it 10 years. That's how I manipulate time. Does everyone follow me there? Okay, so time, whenever it's involved, is going on the x-axis. So I would write here that this would be time, and I would put the units seconds. And then on this one, I would put displacement, and I would put units as well. Okay, a good graph has got to have labeled axes with units. All right, and a good graph should also have a what? A title, yeah. Something like that, something that describes what's going on. Okay, a lot of times people just put position versus time or displacement versus time, and it's like, well, yeah, but that could be for anything. What is it? Your title should also have context or reference to the context of the question. Okay, if I'm looking at this and it doesn't have that context, it just says position versus time, I'm going to go, okay, is that fast or slow for whatever this thing is? Okay, if I was looking at a car, I'd be like, wow, that thing likes bouncing back and forth. That's really weird. Cars don't usually do that. Okay, right? So it's, you got to have some kind of context in there. All right, what else should go along the x-axis here? What's missing? I don't have any numbers there, do I? What do we call the numbers on an axis or a graph? Starts with S. Sometimes you step on one and it tells you how heavy you are. A scale, okay? A scale is a measuring device, okay? On a graph, it's a measuring device that tells you how much is going on here, all right? So we weren't looking at very long here, like each of our intervals was less than a second. So I'm going to just say that a good scale for this might be quarters of a second, okay? So 0.25, 0.5. Obviously, if I was doing this for real, I'd measure and make sure everything was nice and neat. I don't think I need to go past 2 seconds, do I? Yeah, I might have to go past. We'll go to 3 seconds. That should do it. Okay, and then on my y-axis, I should also have a scale. We were looking at things that were traveling like 4 to 6 meters, something like that. So I'd say if we can get up to maybe 8 meters above and below, that should be lots for our graph here. So let's go like this. And I might not have to go very far down into the negatives, but it's important to have it there. I know I did go backwards, so I should have both of that on there. Okay, and now that I've put positive and negative on here, what direction did I make positive? Right. Okay, so actually then I change my units and I add that on there. It's displacement in meters to the right. That way they know that if the number is negative, it's left. Okay, we always refer to the positive direction. Okay, so now I'm looking at this. I got to go back to my numbers. In the first part of the question, we went 3.2 meters to the right and did that in 0.78 seconds. So I've got to plot a point at 3.2 and 0.78. So I'm going to go across. 0.78 is going to be about here. Okay, and 3.2 is going to be about there. Here's a prime example of why we're always going to make our graphs on the computer. Okay, that has got a lot of error in where I put it. It's close, but it's probably not exactly 3.2 and 0.78. All right, so that's my first point. And then in the second part, okay, we went 4.24 meters to the left, and we did that in 0.8 seconds. All right, so I need to go 0.8 seconds along here. Where is my next stop at? What's that? Well, it's probably going to go down into the negatives, yes, but I mean just on the x-axis, where do I need to go to? This took 0.78 seconds, and the next part took 0.8 seconds. Do I just go here, or do I go 0.8 plus where here was? Plus, yeah, okay. I've got to follow on the graph that the next point is 0.8 seconds after this one. Okay, everyone follow me there? Right? I'm plotting this as it's like a story. Here's what happened, and then this happened this long after. Right? So 0.78 plus 0.8 should be 1.58. Agreed? Okay, so that's going to be somewhere around here probably. Okay, and then my y value, I've got to go 4.1 meters, 4.24 meters left of this spot. Okay, so this is 3.2 meters to the right. I'm going to go 4.24 meters to the left now. So where's that going to leave me? Down, below the x-axis, right? I'm going to be in the negatives now, but I got to figure out where. Well, that's not too hard. I'm just going to go 3.2, oh, not 32, 3.2 minus 4.24. All right, so I'm going to end up 1.04 meters below the x-axis. Everyone follow what I did there? Okay. So 1.04, looking at probably right about there. Okay, and then I went 4.1 meters to the right from there, and it took 0.64 seconds. All right, so 0.64 seconds from here, okay. I'm at 1.58 seconds right now, plus 0.64 seconds. It's going to give me 2.22. All right, so I know I've got to go to probably right about there. All right, now I've got to figure out where on the y-axis I've got to be. I'm at 1.04 right now, and I've got to go 4.1 meters positively from there. Okay, so where am I going to end up? Up, yeah, okay. So I'm going to take my negative 1.04, and I'm going to add, whoop, not 1.01, okay, 4.1 to that. So I'm going to end up at 3.06 above. Okay, you guys following what I'm doing? Okay, I'm breaking this thing now down into kind of piece by piece again. Okay, so there's my graph of what happened. Okay. Now, in physics, when we draw a graph, we don't usually connect the dots. Okay, kind of up until this point, that's probably what you've done with graphs, is you put the points on there and then connected the dots. Well, we're in grade 10 now. Connecting the dots isn't going to make any pretty pictures, okay, or anything like that. It's not one of those connect the dot kind of books. Okay, we've just got to figure out what happened in this trip. Okay, where did I start? I would assume, yeah, since it doesn't say otherwise, I would assume I started right here at the origin, 0 meters at 0 seconds. Okay, didn't say otherwise, so that's a safe assumption. Okay, and then I finished over here, right? So what a computer would do with this graph is it would draw us a best fit line. Okay, and a best fit line essentially follows the trend of our movement. Okay, everyone follow me there? All right, so the trend of our movement is that we went from here to there, but we went up and back, down and up. Okay, now in math, they'll probably tell you your best fit line should have equal numbers of points above and below. That's a good starting point for a best fit line. But really, your best fit line needs to follow the trend of your points. My points generally went upwards. Yes, I had this one that was downwards, but in the end, I did finish above X. Okay, so I'm going to draw a best fit line with the line tool. That wasn't cool. Okay, and say it's probably something like that. Okay, I've got 1 point above, 1 point below, and one that's kind of close. Okay, everybody with me there? Right. In the end, what I'm showing you is essentially becoming a dead skill, and that computers will do it for us, and I'm going to show you how you can make them do that for you. Okay, but it's still valuable to kind of see how they draw the lines. Right, we're finding the trend of the points, and they're trying to follow the trend. Now, we calculated that the average velocity of this object was 1.37 meters per second to the right. Okay, I'm betting that the slope of this line would be something close to that. Okay. Now, how many people have ever calculated the slope of a line before? How many people are in math right now and are doing that? Okay. All right. Okay. So the rest of you haven't. This will be new to you, but you're going to get it twice. Okay. The slope of a line tells us how much up it goes compared to how much over it goes. In other words, how steep is it? Okay. That's why it's called slope. Okay. It tells us how steep the line is. But in this case, it's not giving us an angle. It's going to give us how many meters per second. Okay, how many meters per second do we get, okay, in general on this trip? All right, so I'm just going to kind of take the final point on the line. I'm going to take the initial point, which was 0 and 0, and I'm going to take the final point that's on my line here, and I'm going to have to guess because I don't actually have a grid, okay? But it's somewhere around 3, and it's somewhere around 2.25, okay? And I'm going to take that and I'm going to divide those two things, because what I'm doing there is I'm dividing the rise, how much up it went, by the run, how much over did it go. Okay. All right, so when I do that, this is essentially what I'm doing. Okay, 3.0 minus, what was my starting point? 0, right? The y value right here is 0, right? So I'm essentially going 3 minus 0 divided by 2.25 minus 0. Okay, in other words, I'm doing this. Okay, I took two values that were on my line, and I took their I took 2 points that were on my line, and I took their y values and their x values. I subtracted them, and then I divided them. All right. Now, if you look at what this is meters, and this is seconds. So I end up with 3 meters divided by 2.25 seconds. When I divide those two numbers, what units am I going to get? Meters per second. Did I just do a v equals d over t calculation? I did. Okay, because that's what this graph is showing, d and t. Right? It's showing me those two things. Okay, it's showing me v equals d over t here. Okay, so when I do that calculation, that's pretty close to what we got when we did it, right? Okay, that's where your formula v equals d over t comes from. Okay, that's how it was derived. It's most of the formulas that we work with were derived from people looking at graphs and discovering that when they did certain things on the graphs, they were always essentially the same relationship. Okay? They could always calculate the velocity of an object by finding the rise of the graph divided by the run of the graph. So v equals d over t. Okay? That's where we're going to head to. Right now, it probably doesn't make quite as much sense because we haven't talked about the fundamentals of graphing yet. But that's how it's going to tie into v equals d over t. Okay? All right. How far along are we on the worksheet? Anyone on to the second side? No? Okay. Let's work on that for a bit here. Just practice using our v equals d over t stuff and see how we do. If there's any we need to go over, just ask and we'll go over them. Expect that tomorrow your quiz will have 2 problems on it. Okay? And they're going to have, maybe one will be all scalar, one will be all vector, or one will have part scalar and part vector, something like that. But it's just going to be v equals d over t, exactly like you've been working on. Okay? That's what will be on the quiz tomorrow. Okay? And then tomorrow we'll go over your plant projects as well, okay? Because I'll have them marked and returned to you at some point today. Don't worry about it. Yep. Okay, so I will post that quiz later on today, and you can have a look at it. If you're at the net retreat tomorrow, you don't have to worry about the quiz. Okay, but I'll get you on Thursday.